Bismillahirrahmanirrahim. Good morning, everybody. In this lecture, we are going to continue our discussion about how to solve the problem of indefinite integration, how to find the antiderivative of some given function. Uh, Actually, we started in the previous lecture with the integration table, which is basically the opposite of the differentiation table, and then turned our attention to what's called integration rules, which represent a collection of general rules that can help in solving this problem. In this lecture, we will continue presenting some additional general rules that will be helpful to solve this problem. We will start by making a quick refreshment about the first integration rule that we presented in the previous lecture, and then go to two other integration rules. The first rule, which is usually called linearity property, says that if you want to integrate a function that multiplied by some constant, then you can bring this constant outside the integration. And also, if you want to integrate the sum or difference between two functions, you can distribute the integration over this summation or over this difference. And we presented some examples about these integration rules. And also, we mentioned that we can use some additional ideas. For example, we may use long division if we have a rational function where the degree of the numerator is greater than or equal the degree of the denominator. We can start solving this problem by simplifying this expression and use a long division. And also we mentioned that it is very important to use trigonometric identities or take care of using trigonometric identities to simplify the given function in order to be able to solve the problem and evaluate the integration. And we presented different examples in this idea. For example, we present how to integrate 10 square by converting it into 6 square minus 1, and also how to integrate such product by simply using the rule of double angle, and also how to integrate sine, which is raised to power 2. And we finished our discussion with this example, which have some additional idea, which is basically based on multiplying this fraction by the conjugate in order to simplify the expression and get rid of the summation that exists in the denominator. And we mentioned also that you have to read the additional example exist in your textbook in these pages. Now in this lecture we are going to present two additional general integration rule that are to be added to the first integration rule. So we are now going to consider the second integration rule, which is called scaling and shifting property, and sometimes it's called the first generalization rule. In this case, we consider the problem of integrating a function, but in this case, the variable is scaled and shifted. So we assume that we have evaluate, or we have an idea on how to evaluate the integration of f of x that give f capital of x. But now the problem is how to evaluate f of ax plus b, the same function, but the variable x is now scaled by some constant a, and also we have a shift with some constant b. The rule says that the result will be the same function f capital having the same scaling and shift, but you have to divide also by the scalar factor a. And you can simply prove that this rule is valid by differentiating the right hand side. This rule is very important and simplifies the computation or different integrals, and we're going to see now, inshallah. Let's start with this simple example. We want to integrate x plus 1 to the power 10. We know that if it is x only to the power 10, the integration is very simple. Based on the integration table, it will be x to the power 11 divided by 11. But now x is shifted. It is x plus 1. The rule says that it is very simple. You have to write the same output, but scaled. The output was x to the power 11 over 11. So now it will be scaled. It will it will be x plus 1 power 11 over 11. And this can be applied to any similar functions that we have. Any entry in the integration table where we know the integration of this function. If the variable x is shifted, you can simply update the output by making the same shift. Consider, for example, this function e to the power 3x plus 1. We know that the integration of e to the power x equal e to the power x. But now x is scaled by 3 and also we have a shift of 1. The result will be the same. The same function e to the power x scaled and shifted with the same scalar and the same shift. But here, as we have scaling, x is multiplied by 3, we have to divide also by 3. Plus c, of course. Now, as we said in the first integration rule, in many cases you have to apply first some algebraic rules or some trigonometric identities in order to put the given function in a form that is suitable to apply this integration rule. This is very important. In many cases, in many problems, you have to use your background, you have to use your knowledge, you have to use your algebra in order to simplify the given function and put it in a form suitable to apply these rules. For example, we want to integrate this product. We don't have a general rule to integrate our product, but we can use now the well-known trigonometric identity about the sine of the double angle and says that sine x multiplied by cosine x is simply half sine 2x. In this case, we can bring this half outside the integration based on the first integration rule, and now we can say that sine 2x, the integration of sine 2x is the same as sine x, but the output should be scaled by 2 and also divided by 2. So the result will be negative cosine 2x divided by 2. Take care that we apply this integration rule only if x is scaled and shifted, not changed by any other function. For example, we cannot say that the integration of f of x square, for example, equal f capital of x square multiplied by the derivative of x square, which is 2x. This is not correct. Actually, in this case, a is the derivative of this linear function. This is true for only the linear function, not for any other function. For example, the integration of e to the power x square is not equal to the e to the power x square divided by the derivative of x square. This is not correct, and you can prove this by differentiating this side. Now consider this example. We have cosine 2x. This is the example. Cosine 3x multiplied by cosine 4x or cosine 5x. Now we have a product. We have these rules. These rules are very important. These rules are used to convert the product of sine and cosine into a summation, which is very important integration. It can be used to convert cosine multiplied by cosine, sine multiplied by sine, or sine multiplied by cosine. In our case, we have cosine multiplied by cosine, so we choose the first rule. The result based on using this identity will be half cosine the difference between the two angles plus the cosine the sum of the two angles. The difference will be equal to 2x and the sum will be 8x. Now we can simply apply now we are ready to apply the second generalization rule. So we apply first this identity and now we use the second generalization rule. The integration of cosine 2x will be similar to integration of cosine x, but it will be scaled with the same scale and also divided by 2. So the result will be sine 2x divided by 2 and this will be sine 8x divided by 8. Now consider this function. Now to solve this problem, actually we have two ideas. The first idea is to say what 1 minus cosine x based on the trigonometric identities is equal to 2 sine square x over 2 based on the rule of sine double angle. It is equal to 2 sine square x over 2. And now sine square, 1 over sine square is cosec square. And the integration of cosec square exists in the integration table, so we can simply integrate this function. This function is scaled by half, so we have the same scale in the output, and also we divide by half. Actually, this integration can be solved in another way. It is very similar to this expression. this expression, which is 1 over 1 plus sine x. The idea here is to multiply by the conjugate, 1 minus sine x. We can apply the same idea here. We can multiply this function by the conjugate, which is 1 plus cosine x. Now, we have very well-known formulas that appear repeatedly in many integration problems. We know that the integration of 1 over 1 plus x squared equal tan inverse x. This is based on the derivative of tan inverse x. This is equal tan inverse x. In many cases, we face a similar problem, but instead of this one, we have some other constant, 4 or 3 or some other constant. Actually, you can use this generalization rule to make a generalization of such integration. We can prove easily that the integration of dx over a square plus x square equal 1 over a tan inverse x over a. If we put a equal 1, we have the same result, and you can prove that this result is correct by differentiating the right hand side. So now we have a collection of integrations that all involved the inverse function, either the inverse trig function or the inverse hyperbolic function. Inverse trig function, sine inverse and inverse or sec inverse, or inverse hyperbolic function, sine inverse, cosine inverse, and tangent inverse. You have to memorize these formulas. They are very important. The first two formulas are similar. One of them is sine inverse and the other is sine inverse. And also sine inverse is somehow similar to cosine inverse, but or cosine inverse also is similar to sine inverse, as you have to remember them. Also tan inverse and tangent inverse are similar. Here we have plus sign and here we have negative sign, and sec inverse is unique. Remember that in the case of tan inverse and tangent inverse, we have here 1 over a, and also in sec inverse. But in sine inverse, we don't have 1 over a. So if we have such integration, we want to integrate 1 over root, then without x here, then either we have sine inverse, or cosine inverse. If we have 1 over this root, then we have one of these function as the output. But we have a constant minus x squared. This is exactly sine inverse. Sine inverse is some constant, positive constant, plus x squared. And cosine inverse is the opposite of sine inverse. It's x squared minus some positive constant. So we have some constant minus x squared. It is sine inverse. So we have sine inverse x over a. A is the root of this expression, this number, sorry. So it will be sine inverse x over root 5 directly. Very simple. Here we don't have root. So we either have tan inverse or tangent inverse. Tan inverse is constant, positive constant, plus x squared. Tangent inverse, positive constant, minus x squared. We have here positive constant minus x squared, so it is tangent inverse. And we have here 1 over a. A is the root of this expression. It will be 3. So it is 1 over 3 tangent inverse x over 3. In this case, we have 5 plus 3x squared. But in these formulas, x or x squared is not scaled. So we have to remove this scalar. Very simple, by taking the 3 as a common factor. It will be 1 over 3, and then we have 5 over 3. So we have 1 over constant plus x squared. It is tan inverse. And a constant, here we have to take the square root of this constant. So it will be tan inverse x over the root of this constant, and we have also to divide by this constant based on this well-known formula. In this case, this formula is similar to sine inverse. It is some constant plus x squared. X here is shifted and also scaled by a negative. Very simple. If you have shift and scale, ignore it for now, and then you can apply finally the second generation rule to update the final result. So if this, you consider this as x squared, the result will be sine inverse x over a, which is 2. So in our case, we have the same result, but instead of x, we have to put this bracket 2 minus x, and also we have to divide by the scalar of x, constant multiplied by x, which is negative 1. So the result will be sine inverse 2 minus x instead of x, divided by 2, which is the square root of this number, and also we have to divide by the scalar factor of x, which is -1. In many cases, we face integration that very similar to this well-known formula, but we have also x. All these formulas contain some constant plus x square, or x square minus some constant. We don't have x. So what happens if we have x? If we have x, we have to apply first the idea of completing the square in order to put the integration in this form. And then continue as we did in this example. But here, complete square is done for us. But in the next example, we have to do it for ourselves. So in this case, we have x squared and the constant, but we have x also. So we start by completing square. So we write this as x minus half of this constant. So it will be x minus 2 all power 2. If you expand this bracket, it will give x squared minus 4x plus 4. We eliminate this plus 4 by adding minus 4. And then add the original constant, which is a plus x. We simplify these numbers to give plus 1. So now imagine that we have 1 over root x squared. Imagine this as x squared plus 1. X squared plus 1, which is sine inverse, which is sine inverse. But x is scaled. We have to put only the same scale in the output. Is shifted, so we have to put the same shift in the output. Another example, also we have here x, so we have to start with completing square. But x squared have a negative constant, so it is better to start by taking this constant outside. So we have this negative outside. Then we make complete square by taking x plus 1, half this constant, all square. If you expand this, you get x squared plus 2x plus 1. We add -1 to eliminate this 1, and then add -5. So we arrive at this form. We bring the negative into the bracket again. We have this. In this form, we can see that we have 1 over root 6 minus x squared. Ignore the shift now. It is sine inverse. So the result will be sine inverse. But instead of x, we have to put x plus 1 and divide by root of this number, which is root 6. Remember that sine inverse don't have here 1 over a. 1 over a exists in tan inverse and in tangent inverse only. Consider this example. This example, directly it may be seen as a different function. But if you multiply these two expression, x multiplied by x plus 1, you arrive at this function containing x squared and x. So you can start by making completing square. We write x plus half this constant, which is half. If you expand this, you get x squared plus x plus 1 over 4. We don't have 1 over 4. So we write -1 over 4. So now, if we arrange this by taking a negative sign as a common factor, we have constant minus x squared. Constant minus x squared. It is tangent inverse. So result will be tangent inverse. And instead of x, we put this shifted bracket over a, which is the square root of this number. And also in tangent inverse, as in tan inverse, we have 1 over a. So we have 1 over half. If you simplify the expression, you get this final answer. About this second generalization rule, you have some additional example in your textbook, and you are urgently advised to consider this example. They are solved example. You have complete solution of these examples. We have to try to solve this example for yourself first, and then check your answer from your textbook. Now we turn our attention to the third integration rule, which is very related to the chain rule in the differentiation. And actually, it is a trial to make some reversing of the chain rule. Now, if you want to differentiate e to the power x cubed, the result based on the chain rule will be e to the power x cubed multiplied by the derivative of x cubed with 3x squared. So now you expect that the integration of this side will give the original function, which is the exponential function. So if you are asked to integrate e to the power x cubed multiplied by the derivative of x cubed, the result will be e to the power x cubed plus some constant. And you can say that in general, if you are asked to integrate e to the power some function x, which is multiplied by the derivative of this function. The result will be e raised to this function. And you can check very simply by applying the chain rule and differentiating this side that the result is correct. So we can say that in general, if you want to integrate a function g, but it is a composite function, g contain another inner function instead of x, but this function is multiplied by the derivative of the inner function. So the output is actually the integration of this g, but the result will be g of f of x instead of g of x. This is what's called the third integration rule, and somehow it is called second generalization rule. Actually, this term f prime multiplied by dx is sometimes called the differential of f of x. And we say that f prime multiplied by delta x is df of x. Because you can imagine that this term is df of x, and you want to integrate g of f of x df of x. If you rename this f of x and say it u, for example, and this f of x u, so the integration is g of u, integration of g of u du. It is simply as g of x dx. It will be g of u. It is g of f of x. So we can say that df of x equal f prime dx. And you can say also that f prime dx equal df of x. So you can imagine that this derivative, we bring this derivative inside d by integration and say integrate f prime to be f of x and write this df of x. Or you can imagine that we bring this f of x outside the d by differentiation and write it as f prime of x. And we are going to see many application of this simple trick in our example. Let's start with this example. We have x multiplied by e to the power x square. We can solve this problem by saying that we will bring x inside the d by integration. So the integration of x will be x square over 2. This division by 2 is simply taking outside. So it will be e to the power x square dx square, which is simply e to the power x square as you integrate e to the power x dx. Also, you can solve this problem by saying that we have e to the power x square multiplied by its derivative. Its derivative is 2x, but we have x only. It's very simple. We can multiply by 2 and divide by 2 and bring this 2 or this half outside. So now we have some composite function e to the power x square multiplied by the derivative of the inner function. So the integration will be simply the integration of the outer function, the exponential function, and write the inner function as it is. So the output will be e to the power x square. You can solve this way or can solve this way. You can solve this way by writing the expression as some composite function multiplied by the derivative of the inner function. Or you can use this trick by taking this function, which is actually the derivative of the inner function, inside the integration sign. Integration differential operator by integration. And then so you can say now that we have integration of e to the power x square dx square, which is very similar to integration e to the power x dx. Consider this example. We have 1 over x ln x. Now we can say that we have 1 over ln x multiplied by 1 over x. If we now bring 1 over x behind the d operator by integration, so the integration of 1 over x will be ln x. So now we integrate 1 over ln x d ln x. How to integrate? In order to see it more clearly, let's assume that u equal ln x. So we integrate 1 over u du. Very simple. It will be ln u, absolute value. Now we return back to the original variable and replace u with ln x. So it will be ln x. Consider this example. We have sine x multiplied by e to the power sec x over cosine square x. Now we have e to the power sec x. It is a composite function. if we have this composite function multiplied by the derivative of the inner function, the problem is very simple. This is the idea of the second generalization rule. If we have some composite function multiplied by the derivative of the inner function, it will be very simple. So in this case, we can say that we have the derivative of the inner function, because the derivative of sec x equals sec x tan x. And now if you simplify this expression, it will be sine over cosine, which is tan, multiplied by 1 over cosine. So we divide this cosine square into two parts. One of them will be sine over cosine, and the other will be 1 over cosine. Sine over cosine will be tan. 1 over cosine will be sec. So this expression actually is the derivative of sec x. So the problem is very simple. It's very simple. So we can bring this sec x tan x inside the d operator to be sec. Now we have sec here and sec here. This is the idea. If you have sec here and sec here, it is simply as u. It is x as x. So this is exactly as you integrate e to the power x dx. It will be e to the power x. But instead of x, you write sec x. So this is the basic idea of applying the second generalization rule. You have some composite function, but multiplied by the derivative of the inner function. In this case, we have cosine x divided by 5 plus sine square x. In this case, we can say that we have this rational function 1 over 5 plus sine square x. But here we have sine x. It is somehow complicated. Instead of having 1 over 5 plus x square, this will be more simple. But we have 1 over 5 plus sine instead of x. But actually, you have the derivative of this sine, which is cosine x. So the problem is very similar as this was x only instead of sine. So as we have the derivative of this sine x, which can be considered as the inner function, the problem is very simple. So we can solve this problem by bringing this cosine inside d. What is the benefit of making it? We can now consider sine and sine as x. It is the integration of, if we name sine x u, for example, so the integration will be du over 5 plus u square. 5 plus u square, which is tan inverse based on the well-known formula. Based on the well-known formula, it is tan inverse. It will be tan inverse u over root 5 multiplied also by 1 over root 5. And then we put u as sine x. So this is the basic idea of the second generalization rule. And take care that if you want to take some expression behind the d operator, the benefit of this, and when this is helpful in solve the problem, if this new function appear behind d, exists also in the expression. This will simplify the problem. If we bring some function by integration inside the d operator, this will be helpful and will be a good step to solve the problem if the functions that appear behind the d operator exist also in the expression. If you name this u and this u, this will in general simplify the expression. Consider the example sec square over 2 plus tan square. I think this is clear because now we can say, it is sec power 4. If it is sec power 2, we can bring this sec square to be tan x. But now this is sec to the power 4. How to deal with this? So we separate this into sec square multiplied by sec square, and take one of these sec square behind the operator. So it will be tan. What is the benefit? Because we have tan here and tan here. This will simplify the problem by naming it u, for example. But we have also sec square. We have to modify this to be tan. It is very simple by using the identity. Sec square will be 1 plus tan square. So now we can name this function tan x as u to simplify the expression, or y, for example. So we have 1 plus y square over 2 plus y square. This is very simple expression and can be solved as we illustrated in applying the first generalization rule. You may add 1 and subtract 1, or you can make long division. So if we make this by adding 1 and subtracting 1, if you add 1 and subtract 1, now this bracket will be 2 plus y square over 2 plus y square, which is 1. And this will be 1 over 2 plus y square. The integration of y dy will be y. The integration of this expression is exactly tan inverse. It is tan inverse. It will be tan inverse y over the root of this number, also multiplied by 1 of root 2. And now we have to return back to the original variable by replacing y with tan x. Consider this example. We have many e to the power x. In this case, we can bring e to the power x behind the d operator. Why? Because now we have e power x here, e power x here. But we have here e to the power 2x. We can write it as e to the power x all raised to power 2. Now we can rename e to the power x with some other variable, y for example. So the expression is 1 over root y squared plus y squared plus y. This is simpler to compare to the original expression. But how to solve? Actually, we faced a similar problem. We had 1 over root y squared, but not plus constant. It is plus y. We have to apply the idea of completing square. So we complete square to get this expression. Now we have 1 over root. Imagine this as y. It will be y squared. The shifting is very simple. Y squared minus some constant. It is cosine inverse. It is cosine inverse. So it is cosine inverse this y, shifted y, over the root of this number. And we return back to the original variable by replacing y with e to the power x. Based on this second generalization rule, we have very important well-known problems. We have two well-known problems. The first one says that if you want to integrate some fraction, and in the numerator we have some function, and in the numerator we have another function, but they are related. Actually, the function in the numerator is the derivative of the function in the denominator. The rule says that the integration will be actually ln the function in the denominator. If you have to integrate f prime over x, the result will be ln f of x. And it is very simple to prove this by either differentiating the right hand side or saying that if you bring this f prime inside the operator by integration, it will be f of x. And now we are going to integrate 1 over f of x df of x, which is similar to integrating 1 over u du, which give ln u. This well-known problem is very important and appear in many integration problems. For example, let's start with integration tan x. We know from the integration table that the integration of tan x equal either ln sec x or negative ln cosine x. We now say that based on this well-known problem, you can see how we get this result. We write tan x as sine x over cosine x. So now the derivative of this function in the numerator, which is cosine x, is negative sine x. We can update this sign to be negative sine x by adding negative sign outside. So now this function is on the form of this expression. This function is the derivative of this function. So the result will be the ln of the function in the denominator. So we have negative sign here. We have also negative sign here. Now, if we have, for example, x over this expression, when you have a rational function, always remember this rule. Can you put the function in the numerator, the derivative of the function in the numerator? If you have, in general, fraction, try to check this rule. May solve the problem or solve at least part of the problem. Now, the derivative of this function is 2x. We can modify this simply by bringing it to x, by multiply by 2 and divide by 2. So now this is the derivative of this. So the result will be ln x squared plus 1. If you have this expression, you can say that we have a fraction and we have to check first the derivative of this function. The derivative function will be 0 for 3. And here we have a product. The derivative of this product will be x multiplied by the derivative of ln x, which is 1 over x, plus ln x multiplied by the derivative of x, which is 1. So it will be 1 plus 10x, which is exactly the numerator. So without any modification, the derivative of the denominator is the numerator. So the result will be ln the function in the denominator. Consider this example. We want to integrate this fraction. We check first the derivative of the denominator. Derivative of 5 equals 0. Derivative of sine squared, it will be 2 sine x multiplied by cosine x. Now we check the numerator. It will be the same function instead, except that we have to multiply by 2, which is very simple. Multiply by 2 and divide by 2. And now the result will be ln the function in the denominator. Consider this example. we have a fraction. We start by checking the derivative of the function in the denominator. The derivative of the function will be 0 for 2. The derivative of this exponential function will be the same exponential function multiplied by the derivative of the exponent, which is 2, multiplied by the by len the base, which is len 3. Now check the numerator. We have this function 3 to the power 2x, and we are missing this constant, but it is very simple to add this constant. But we have here an extra power, negative one. How to do? How to deal with? We have to separate these powers by writing it as 2 to the power 2x multiplied by 2 to the power negative 1. 2 to the power 2x multiplied by 2 to the power negative 1. 2 power negative 1 is 1 over 3, and we bring it outside the integration. Now, this expression can be simply converting into the derivative of this expression by multiplying by derivative of 2x, which is 2, and also multiplying by len 3 and dividing by them. Dividing by 2 and dividing by len 3. Now we have this expression to be the derivative of this expression, so that will be the len the function in the denominator. Consider this example, and also we want to apply the same idea. Now if we check the derivative of the function in the denominator, you can say that the derivative of this function, derivative of this function in the denominator is not exactly the function in the numerator, because the derivative of the function in the numerator will be 6x to the power 5, but we have this extra term x squared, but we have minus sign here, so we can divide this integration into two problems, x power 5 over this expression, where we can apply this rule, and then see how to deal with this extra problem. So in this case, we can say that by multiplying by negative 6 and divided by negative 6, this function will be the derivative of this function, so the result will be len the function in the denominator. Now we have this extra problem, x squared over x to the power 6. We cannot say that the derivative of this is the function in the numerator. But now if you think that we can bring this x squared inside the d operator, it will be x to the power 3. What is the benefit of this? This will be helpful if this x power 3 appears also in the original function, remaining function. But we have x to the power 6. But we can write it as x to the power 3 raised to power 2. So this is x power 3, and this is x power 3. So we can say this is u, and this is u. And this will greatly simplify the expression. So we can say that this is 1 over 4 minus u squared. 1 over 4 minus u squared. And this is exactly tangent inverse. This is exactly tangent inverse. So if we have 1 over 4 minus y squared, it will be tangent inverse u over 2 and also divided by 2. And then we replace u by x to the power 3. Actually, you can check this problem in your textbook, which contains similar idea. What is the idea? The idea is that we have to divide this problem into two problems. For example, in this case, we have to divide it x over this expression and apply this rule by adjusting or modifying the numerator to be the derivative of the denominator. This is for x over this expression. But we have extra problem, which is 1 over this. We cannot apply this well-known problem, but it is solvable. 1 over this expression can be solved by a similar idea, but we have here to apply first completing square and then use one of the inverse trigonometric or hyperbolic function. So the idea in this example is that you separate the problem into two problems. One of them can be solved by this well-known problem, and the other problem can be solved by some other technique. So we can apply this well-known problem for the part of the given integration problem. Now consider this problem. Actually, this problem can be solved using different ways. We present two ways. Now we have 1 over 1 minus e to the power x. Actually, the derivative of the function in the denominator is negative e to the power x. It doesn't exist e to the power x in the numerator. So we start by multiplying numerator and denominator by e to the power x. So arrive at this expression. Now we can bring e to the power x inside the d operator. So we have here e to the power x, e to the power x, and also e to the power x. So if we replace e to the power x with y, for example, we arrive at this expression. And this problem was solved somehow before. We have 1 over y plus 1 minus y. If you multiply these two brackets, we arrive at y square minus y, or y minus y square, and then take negative in the outside. So now how to solve this? We apply the idea of completing square. So we have 1 minus half all power 2 minus this expression. Imagine this as 1 over y square minus 1 over 4. So it is very similar to applying tangent inverse instead of making some shift, which is y minus half. And then we return back to the original variable, which is e to the power x. So now this is an idea to solve this problem, but actually when we solve this problem, we didn't use this well-known problem. But actually we have another idea to solve the same problem, which uses this well-known problem. Instead of multiplying both numerator and denominator by e to the power x, we multiply both by e to the power negative x. Why e to the power negative x? In order to get a more simplified expression in the numerator, instead of having multiple e to the power x, if you multiply by e to the power negative x, so the expression in the numerator will be only 1 plus e to the power minus x, because e to the power minus x multiplied by e to the power x will be 1. So now you can say that we can adjust or modify the numerator to be the derivative of the denominator, because the derivative of the denominator is 0 for this, negative e to the power negative x for this. We have e to the power negative x, but the missing constant is negative 1. We can simply multiply by negative 1 and also add negative 1 outside. So now we can apply this well-known formula. We can say that the numerator is the derivative of the denominator, and so the result will be length the function in the denominator. Also try to solve this problem using a third technique by adding e to the power x and subtracting e to the power x. Try to solve the problem using this idea, and after this, of course, you have to separate it into two integration: 1 over 1 minus e to the power x over 1 minus e to the power x, which will be 1, and also e to the power x over 1 minus e to the power x. Try also to solve this problem, and actually the solution exists in the textbook, and if you have any problem you can contact me, and you can solve this problem using similar ideas. Actually, not all these 3 ideas can be applied to solve this problem, but try to solve this problem use one of these ideas and see how to solve it. The second well-known problem based on this second generation rule is similar to the first one, but now we have an extra root in the denominator. The result will be 2 multiplied by this root. This is a double root, double this root. So you can in general check if you can use this well-known problem if you have a fraction containing a square root in the denominator. So what you are going to check, we are going to check that the function in the numerator is the derivative of the function inside the square root in the denominator. The derivative of this function is 2x plus 2. So we can simply multiply this expression by 2 to get 2x plus 2 and divide by 2, of course. So now this function is the derivative of this function inside the square root. So the result will be the square root multiplied by 2, which is very simple. What about this problem? If you try to check what is the derivative of this root, it will be 2x plus 3. We can simply convert this or modify this to be 2x multiplied by 2 and divide by 2. But we get now 2x plus 2. We have to make it plus 3. How to do this? By adding 1 and subtracting 1. As this. So multiply by 2 and divide by 2, of course. So we get 2x plus 2, but we need it to be plus 3. So we add 1 and minus 1. So this term, this part of the expression over this root can be solved using this well-known problem. The derivative of this expression will be the expression. But we have an extra problem here, which is negative 1 over this root. We have to deal it with some other technique, not using this well-known problem. So we divide into two integrations. The first one is solved. It is this root multiplied by 2. And how to deal with this? It is 1 over this root. Very simple. It is x squared plus some constant, but you have extra x. Extra x means you have to do completing square. So if you make complete square of this expression and apply the formulas of the inverse hyperbolic function, you get it as cosine inverse, and you have to check it yourself. A second problem, which is this problem, x over this root. Also, if you try to check the derivative of this function, it will be 2x minus 1. We can modify this to be 2x, but we have to add minus 1 and also plus 1. And we apply similar idea by separating into two problems. So we multiply by 2 and divide by 2, and then add 1 and then subtract 1. So now we divide it into two problems. 2x minus 1 over this root can be solved using this well-known problem. It will be this root multiplied by 2. But this expression, how to deal with? It is 1 over root x squared minus x. Very similar to the previous problem. Make a completing square of this and then use the formula of cosine inverse. We end our discussion of this rule by this final example. And also this example have a similar idea that you can check in your textbook. In this case, we can say that how to deal with this complicated function. We start first to simplify the expression somehow by saying that here we have x squared. If we bring this x squared beside the operator, it will be x to the power 3. Is this helpful? Yes, because we have also x to the power 3 here. What about x to the power 6? We can write it x to the power 3 power 2. So we have x to the power 3, x to the power 3, x to the power 3, name it u. So now we have tangent inverse u over 2 multiplied by 1 over 4 minus u squared. It is still somehow complicated. But if you take care of this expression, you can see that this tangent inverse is multiplied by this function. And actually, this function is the derivative of tangent inverse. Is the derivative of tangent inverse. So if you bring this expression behind the operator by integration, it will be tangent inverse. It will be tangent inverse u over 2. So now we are integrating tangent inverse d tangent inverse. Very similar to integrating x dx. You have to increase the power and divide by the new power. So the idea here is that we have to bring some expression inside the operator twice. We have to bring some expression inside the operator twice. And you can check similar idea for this problem. As you see many times in this lecture, it is very important to consider the additional example exist in different section of your textbook. For this third generalization rule, you have to check the additional example exist in this collection of paper. And this is the end of our discussion of how to solve the problem of indefinite integration. And actually, this problem we will have a continuation in Math 2 by saying how to deal with this problem, how to solve more involved integration problem using what's called integration technique. But for our case in Math 1, that's all by introducing integration technique and how to deal with some problem using the three integration rules that we have discussed in this lecture and in the previous one. That's all for indefinite integration, and the remaining lecture with lecture number 12 will be about definite integration. Thank you very much.